Alright, should be streaming, whatever. Making a video, really. That's all we're doing, really. But whatever. We're making it in some streamy way. Yeah. Anyway. So, let me just. What else do I have to do? There's probably some other little detail. But we'll just go to the relevant video. Alright, so the Iron Gosling guy has made another video just repeating the same thing with what he calls a quick release, which just is a mechanical release. It's not a quick release. And of course we can't see it actually how it functions, but it's really just he's just basically replaced his finger with a mechanical device and therefore said it's a quick release when no, it's just a mechanical release. And you can see the springs are actually moving, with his, whatever you call it, his experiment. So if you look closely enough, when he launches, the spring ends up way up here. The springs are being launched as the objects are. Which, again, I pointed out would probably be a good idea to tie the springs together because they probably don't have the same spring constant. They're like used valve springs or something. And so, they might not have the same springiness and therefore are absorbing the pressure unevenly and therefore are, launching each other, which isn't what you want to have happen. But anyway, so he's proved again that there's no conservation of momentum, that there's something called conservation of energy. Alright, so this is what he wrote. Draft science claims the half mass will go twice the velocity. I claim that's what actual physics says. Professor Lewin said it. Okay, he drew the equation pretty much defining it. When they say, M1A1 has to equal M2A2, they're basically telling you the acceleration it will end up being a velocity, and they're basically just saying mv has to equal mv. And it would be ridiculous to say they meant by acceleration that there is no acceleration difference, because the faster you accelerate in less time, and therefore there's no acceleration. Obviously he wasn't saying that, but anyway, twice the velocity preparing 4 times the height. Yes, that's what will happen if you do the experiment correctly, because that's how springs work. So if you're not within the tolerances of the spring, it won't work because the spring constant breaks down. Now that's already been illustrated a few times. The line sort of goes this way, a little bend at the beginning, then very straight, and then a little bend at the end. So if you go into those bendy bits, well, then you don't know what you're going to get as results. But if you stay in the straight line part, it works. Okay, so he says, science says it will go 1.4. Now, there's not a single fucking video, not by a single lecture, a single science video, a single any kind of video, not a Veritasium video, no video showing this 1.4 thing. So we don't have any evidence science says it at all. Zero. And we're all supposed to believe it, though, because they say so. These 5 lunatics say so. Yeah, that's it. That's their evidence corroboration, is they can't produce a single video by a single scientist actually saying what they're saying science says. So, and I'm supposed to believe. Hilarious, really. It's just ludicrous. So they say science says it will go 1.4. Where does science say that? Where? Could you just please link me to your video? Just please link me to one credible physicist saying that. As fast as only twice as high. So science wins, he says. I don't think science is winning. I don't think you're on science's side. I don't think you even know what science is. Science isn't that you do some wacky experiment that's a complete aberration from the known reality and then claim you have debunked all of science. So I have done this previously. We'll do it again. So all right. So yes, he did the experiment differently, different amount of pressure, different this, different that, blah blah blah. Who cares? And obviously the quick release is just a mechanical release. It's not a quick release. So let's just show some of that. So we can't see any of that. So instead of taking a little bit of time and just moving the camera and showing us the thing that actually does the compression of the spring, so we can actually see what kind of condition the springs are in. We can see the quick release. No, it doesn't even bother doing 2 minutes of that video, so we can at least see the mechanism he's using. So it's just a mechanical release. So it's the same thing as releasing it with his hand. He's just moving a device that slides over, and he's just moving the device. He's not pulling it with a string so he could go faster. He's not doing it some way. Now, we've shown the videos over and over. The Mythbusters used a string and then scissors. Professor Lewin used a blowtorch. Another guy used a match that would burn the string. So we have all these examples of a quick release, and his doesn't look anything like one, does it? No, it doesn't. So the whole point is you're supposed to gain some leverage somewhere. You see, even if you made your quick release with a lever, the idea would be is the end of the lever moves twice as fast, and then if you make it a 4 to 1, then it's 4 times faster. See, that's how you do it. You use leverage, but you don't understand how a lever works either. So yeah, you can't accomplish the task. So as stated, here's a spring all the way up here. You can see that, right? Probably. Yeah, my mouse is there. See, way up here? There's a spring up here. It's not supposed to be there. That's not a good thing. And there's a spring here. So his springs are going with the energies to some extent. The energy obviously isn't going into the object because it's clearly the springs are expanding in free space. They're flying in free space. That's obviously evidence of their weight. They're absorbing some percentage of the evidence, the energy of the experiment. So it's not a good sign right on its face. All right, so let's jump ahead to the twice as fast. We'll see how far one of the springs goes here. Who cares? But I mean, so that's twice the. Essentially, the spring will now move twice as fast, because the object on top of it is half the mass. So it's going to try to go twice as fast, twice the acceleration. Okay, that's what the plainly Professor Lewin said, twice the acceleration. He didn't mean, well, twice the acceleration, but it's going twice as fast, so it's the same acceleration. That's clearly not what he was saying, and he certainly didn't say anything like it goes 1.4. Fuck. Alright, so it looks like a spring is all the way up here. So right behind it is a spring flying. Yep, the spring went all the way up. So not too good. Alright, so we can't even figure these little details out. That if the springs are flying up there, that means the energy is not going into the object, it's going into the springs. Which probably isn't the way you want to do the experiment when you're trying to measure how much energy goes into the object. So anyway, crappy quick release. The springs aren't tied together. The springs are not mounted to the floor. That means they can just launch. And so lots of defects in this experiment. And besides the fact that he doesn't have this marked off in the same units of distance. So we can't tell from how much the angle is fucking this up, but clearly this unit of distance from the compression to this first line isn't anywhere close to the 1 unit of distance. So the whole thing is shitty. Alright, but now let's just go look at the brozo of it. So these two videos, so this group of 5 morons who say this is what science says, have produced these different results in their videos. So Brozo did the experiment just using a lever on a spring. Exactly the same, right? There's no logic that would say Brozo's experiment was broken in some way. That it wasn't doing just the same exact thing, just measuring the force from the spring. The spring's compression was providing all the energy, and the objects end up with it. And you can see it repeated over and over again. Turn the sound off. Well, see, that's both together on the lever at the same time. All right. And obviously the thing twice the distance has to move twice as fast. Now what you'll find is that, yes, when he actually does them individually, the results are just as obvious. It's just as obvious this is moving twice as fast. So let's just get to that part. Both together. We don't want to do any of that. Ooh. gross. I don't know why this one's sideways. Let's just play this a little bit and see. I don't know what all that is. Ugh, yeah, who wants to look up your nose, you fucking retard? Alright, separately, release line 0. So this should be, I guess, it's going to be all in slow motion or something. I don't know. Nothing's happening. Yeah. Do, 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 do. There it goes. Okay. So eventually he lets it go. Alright, I don't need, well, fuck all this crap. Let's go back to the beginning and hope we have a better image. See, you can't just post experiments. You have to do all this crap. You know, let's read this. Excess lever mass probably accounts for not being closer to x.4. So that's crazy, frankly, but whatever. So it wasn't anywhere near 1.4, okay? It wasn't that it was a little off. It was way the fuck off. Alright, going really fast. So again, if it would be nice if he just did the experiment and showed it so we could just see it, blah, 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 blah. So this should be somewhere near. Okay, so there's the 2 mass. So there's the slow motion of the 2 mass. Okay, so you can sort of get the feel for it. Bang, 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 bang. Okay, now here's the yellow one. Bang, bang. Bang, bang. Right, I mean, obviously going twice the speed. Okay, so his numbers were 19 and 11. So this took 11 frames to make the trip. The other one, slow one, took 19. Very, very close to 2 to 1. And, yeah, so, okay, so here's your evidence, these morons. They're both saying science says this thing. Clearly the experiment isn't showing the thing in this example at all. I mean, nowhere close. Just as a side note, I'll throw in, I mean, I did one of these experiments just because Brozo was saying this silly thing, and I said, well, I guess I better go test it. And yes, my results were, well, the first time I did the experiment without a quick release, it was like 1.6, you know, and then when I built a quick release, it went up to 1.88 or 87 or some kind of number like that. So getting close to 2 to 1. Now the reason I would suspect I couldn't get 2 to 1 is that you know, I was actually using 2 physical objects, you know, on one side, you know, and then one object on the other trial, and obviously pushing 2 things is a little different than just pushing 1, so blah 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 blah. But anyway, so I mean, that's the history. You know, that's the reality here. And these goofballs, you know, just keep doing this crap of saying physics says, science says, when no scientist says it. So I'll play another boring, you know, lecture video, and we'll go over it again. And yes, they always use the word acceleration because they're glued to that concept, because that's the only way they can shove the per second thing in, and they need that for their kinetic energy theory. All right, but the fact is that physicists think, okay, half the mass, twice the velocity. That's what they think. All right, so don't tell me science wins and science says, but you don't have any evidence science says any of that crap. So it's just a despicable lie to say you're defending science. All right. So it says, can't reason with the unreasonable. That Gary dude just doesn't get it. Why should I get it? There's no theory. There's no explanation of it. There's no evidence of it. There's no experiments proving it, except for these that completely contradict each other. So what aren't you getting about the complete contradiction between their experiments? What aren't you getting about how that's a problem? Yeah, okay. Yeah, I could ask the question, but they won't answer any of them. I don't think there were any other comments here. Yeah, it doesn't look like it. So John Walker says, thank you very much for uploading the new video, Ian. Your experiment shows clearly that the spring stores energy but not momentum. It doesn't store MV. It doesn't conserve MV. That's what you're demonstrating. That somehow, okay, momentum doesn't get conserved when all the physicists say it, right? I mean, you can go over it and over it and over it, and the physicists all say conservation of momentum is a thing. You have to conserve the momentum. Again, I can just recite Professor Lewin again. Nature can't finagle momentum. What do you think he meant by that? That nature can finagle it? Oh, I mean, this is so fucking pathetic. It's amazing that you have to argue with these people. You play the quote, they don't care. They don't care that the physicist says it. They'll sit there and lie about what he just said. I mean, it's, you shouldn't have to argue with people this dishonest. All right, the speed of the half-mass probe is only v2 times the speed of the one-mass probe. See, now does that make any sense at all? v2? Oh, the square root of 2 times. So again, yes. So, and who says that? What physicist says that's what it comes out as? Where is that? Where's that example? That's how springs work. That Hooke's law is really a pile of shit, and it really isn't linear. Okay, and it doesn't weigh. I don't understand how you can keep arguing this. Anyway, not twice the speed, as Goofy would think, as all the other physicists say. So let's just understand, all the lectures say so. You're the only people saying not. I mean, the exact words of Professor Lewin are twice the mass, half the velocity. So v equals x squared. Right, and I'll show you the college professor doing the equation through momentum where there's no squared here. Okay, so, all right, is the equation for the velocity. No, that's the equation for the acceleration. But regardless. All right, mindless marbles. Let's see what kind of crap he says. Very good precision. So it completely contradicts Brozo's experiment. Has nothing to do with any physics video you can link me to. So you can't link me to a single physicist actually saying this is what you should expect. 1.4. And yet it's very good precision. Again, this is how much respect they have for science. This is a great improvement over the previous tests. How exactly so? The springs are flying up, shooting up as far as the object is going. How exactly is that an example of great improvement? Okay. On my screen, I measured a length of 6.5 centimeters for the first and a height of 12.5 centimeters for the second half-mass object. Right, and Brozo measured 19 and 11. 19 and 11, that's what Brozo measured, okay, for the speed. Okay. It shows pretty clearly that wasn't shooting into gravity. So this doesn't understand. The one experiment is shooting into gravity, the other one isn't. So the other one is just measuring what's the velocity of the objects after the spring is done with them, okay, and it shows it pretty close to a 2-to-1 relationship on the velocity. Obviously, when you're shooting into gravity, you're measuring the velocity based on how high it goes, and twice the velocity will go 4 times the height. It shows pretty clearly that Gary is wrong. So this is all they need. So all of science can say one thing, all the other experiments can show something else, and all they need is their one raggy piece of shit. And just like a flat earther, they'll say, well, because I took a fuzzy picture, there's Sasquatch. He exists. By his own proposed experiment. Yes, I'm proposing that the fact is, if you do the experiment correctly, it will prove the point. Brozo did it pretty close to correctly, so he came pretty close to getting the right answer. It should go without saying it helps to play at 0.2x the speed. Okay. This is exactly the kind of experiment Gary asked for with exactly the request he asked for, quick release mechanism. So he doesn't understand what quick release means either. It doesn't mean mechanical release. See, my first, okay, that's just the truth, that when I was making a quick release, my first quick release, I realized the little string was sliding off the thing, and I didn't really want that. I didn't want it to move, and so I had to make it even shorter, so the quick release was, in fact, a quick release. So, I mean, it's not exactly, you can't even get the science of a quick release mechanism correct. It's not a quick release to replace your finger with an extendor. That doesn't change the quickness of the release any. Putting on fake fingernails doesn't do it. All right, there are experiments and arguments that demonstrate him wrong. Please show me those, okay? Show me one not done by one of you assholes, okay? Show me an experiment not done by the cult members that demonstrate this phenomenon. He simply refuses to consider this. Consider what? The infinitesimally small volume of evidence you can point to? Yes, I simply refuse to consider infinitesimally small amounts of evidence. Okay, and some of his most fanatical followers. So all you have to do is just suggest they are wrong and you're a fanatic. Okay, just want to do some kind of strange cult of personality worship. So again, bizarre statements when they're worshiping each other. They're calling each other doctor. Yeah, I mean, it's hilarious. I mean, none of my followers are calling me doctor. Oh, hilarious. It's just, I mean, these comments are so funny, which is incredibly ironic. No, you're incredibly ironic, you silly person. Oh, you should write a book. Okay, because that's as irrationally religious as you can get. So clearly here they are, this little cult of five kooks defending a theory that absolutely no physicist endorses or can be, you really have to work to force them to say 1.4. They're clearly not saying it. Okay. None of them take any of this crap seriously, so clearly they're the ones actually shitting on science. They don't care about the truth whatsoever. Clearly these people don't care about the truth. I mean, it's been repeated to them 17 times. It's all over the time. Once, twice, 3 times. Go over and over and over this contradiction. I've pointed out the complete contradiction between these two experiments, and what have they said about that? Have they said Brozo's experiment was a piece of shit? What have they said? They said nothing. Brozo said his own experiment sucks, okay, and he said he has a perfect one, but he won't show it to us for whatever reason. Okay, they just want to play sides. Yeah, whatever. It's so grotesque. No, you're the monster here, the disgusting, distorted, ugly, slobbering pig monster. I can't believe people can be like this. You're the one posting people's personal names and shit. You're the one playing all the games, asshole. You're the one showing yourself to be the one with no argument. I wonder if anyone will come out and admit that, yes, experiments do contradict Gary. So exactly what experiments do that? So where's your volume of experiments? Where are the experiments? Let's just list the experiments that prove it, and then let's list the ones that disprove it. Yeah, I don't know how much more clear this can be made. How is this at all clear? I mean, I just showed the two conflicting experiments. One says 1.8, one says 1.4. I mean, those numbers aren't really close. If Gary were honest, less narcissistic, he would look back and revise his own incorrect concepts. I mean, what's the concept? I think conservation of momentum makes perfectly good sense. All the other physicists say it makes perfectly good sense, and you say I shouldn't believe in it for some dopey reason, that you can create and destroy momentum. I'm saying, well, I don't think you can. I don't think NASA thinks you can. I don't think they land on the moon thinking you can. So why don't you just explain to me how the lunar module works? So just explain to me, okay? It was all just about releasing gas. They didn't even use fire, to land. So all they're navigating with is puffs of gas. And all they did was say the gas has a certain mass and has a certain velocity, and that defines its energy. I'll get exactly the opposite reaction when I let that go. I've changed the bias of my module, and I will move. And they didn't square any of these things. They weren't using kinetic energy. So why don't you just explain to me how it does work with kinetic energy as the proper theory? the 1.4 theory? Why don't you show me a NASA engineer explaining the 1.4 theory? That would be called evidence. That would be called experiments. But instead you just lie and pretend you've made a credible argument when you've made an incredible argument, not a credible argument. You don't know the difference between incredible and credible. Let's see, I don't know how much more clear this can be made. I mean, to call this clear, two completely contradictory experiments, and he's calling that clear. Completely contradictory experiment. Okay, that's clear. I mean, what a liar. Alright, if Gary were honest, less narcissistic. Okay, yeah. I mean, again, revise it with what? There's nothing to revise. It's just absolute nonsense. I have to revise anything. Oh, look at this. Brozo only typed one little tiny paragraph. Oh. I often wonder what goes on in Gary's mind. So they can't make a real argument, so this is all they can do. I don't wonder what goes in your mind. You're a pervert, first off, a disgusting one. Okay. I mean, no wonder you're sick a lot. Okay, if he has one. Okay. It must be like being hypnotized by a strange hypnotist, a stage hypnotist. See, everything's a show to him. Everything's about some vaudeville thing. Like that was vaudeville. Where they had the women with like the preposterous breasts would pop out and jiggle them, and that would make the men go, ha ha ha, I go all horny. Hilarious stuff, really. You'll watch it and just say, that turned somebody on? Woo. I mean, it's just so fucking... Why don't you just go to the farm and actually go to the real pigs? Why don't you just go to the pig pen, and have a wank? Okay, into being unable to recognize, say, the number 5. What the fuck? When counting to 10, always missing the number and think... So he thinks hypnotism is a real thing. So that makes him very credible, right? He believes in 1.4, and he believes hypnotists really do hypnotize people. Jesus Christ. Jesus Christ. He's insane. Okay, poor guy. Poor us for having to listen to him occasionally. So let's look at that, So that's his big reply to the fact that, okay, there is this real question out there. They really think it's just so sewed up. They sewed it all up. They've proven that there is no conservation of momentum. Springs never, conserve momentum. They just produce this 1.4 crap. Okay. Just amazing. All right, anyways, John Walker. The free energy nut. On the nail, Stephen. I think Goofy is unable to grasp a complete sentence. Whatever that is. I can understand the sentences that came out of Professor Lewin's mouth. You apparently cannot. Okay. She only sees 1 or 2 words of the paragraph. So isn't this all so very interesting? When she watches a video. He keeps doing this she thing. Again, like... So these are all these politically correct fuckers. Right, playing their little game like they're the great defenders of women or the this and that. And he keeps saying like he's going to insult me by calling me she. Okay, so he thinks being a woman is a lesser form of human life. Oh, just it's the amazing, this irony. The irony is so thick. She, and obviously this is a little tiny person. He's one of those little short people, right? There's that song, short people, blah, 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 nothing to live for and all that kind, should jump off a cliff. He's one of those people, He's just a little petty short person. All right, she doesn't understand that she is looking at, debunks what she herself said yesterday. So nothing is debunked. But anyway, except themselves. They only debunk themselves by lying about what the circumstance actually is. What they have actually proven. So again, conservation of energy, not momentum. So even though all the physicists say conservation of momentum, he decides to do this. Professor Lewin overtly says nature can deal with kinetic energy one way or the other. But nature can't finagle momentum. So that's the statement. And he just keeps, I don't have to account for that. I'll tell you what Professor Lewin really said. He said 1.4, even though he never did. All right. So that's the game he's playing, the liar. The pathetic, horrible, evil liar. All right, so we will go to one of these Yale lectures that are, I have to concede they're a little boring, but whatever. I mean, he's not as interesting as Lewin's. More antics, more experiments, so it's a little bit, less of a tedious chore to listen to, but whatever. We'll see if we can get somewhere in pointing out that here's another physicist, certainly implying, if not overtly stating it. Okay, and that's the, I have to go through each one of them, and I'll find where each physicist does his description of the circumstance. And that's all the best I can do, But I mean, it's got to be out there somewhere where they overtly do the experiment or they overtly make a statement, but that's not what we have so far, unfortunately. All right, so let's see what we got in this little jibber jabber. Gus. Oh, that looks like somebody new, but it's probably just Farley the Troll, but let's see. All you have to do is get off your lazy arse. So he's one of those people. Open into any physics book. Well, why can't you link to it? The internet's got all the physics books in it, so why don't you just reference it with a link? That gives you the basic formulas. The formulas are what exactly is being in dispute, okay? The book says MGH. I'm clearly saying that's a lie. That won't get you the right answer. It's MGT if you want to get the right answer, okay? The amount of energy something has falling in gravity is MGT. 9.8 meters per second. It says per second. It doesn't say per inch or per foot or per meter or per mile. It says 9.8 meters per second. It's how long you fall in the gravity that matters. Sorry, you're really stupid. See, if I already have a velocity, coming into the Earth, all I'm going to get from the Earth's gravity is the number of seconds I'm in the gravity, right? So we know that it's pretty weak as you go far out, and that the asteroid could be going 10,000 miles an hour, and so therefore it's not going to be in the gravity very long. But let's say it's in the gravity for a full second of meaningful gravity. All it's going to get is 9.8 meters per second of extra velocity. So it's going 10,000 miles an hour plus 9.8 meters. So it's only 10,009.8. That's how much its velocity was increased. An infinitesimally small, meaningless percentage. You idiot. Now, even though it traveled a gigantic distance, it only got 9.8 meters of increased velocity. That's the truth you are lying about. All right. Okay, then you'd know what is or isn't predicted. So again, I showed the math in the video where Professor Lewin did the math. He drew the equation. Their argument is when he said it's twice the acceleration, he didn't mean it was twice the acceleration. He meant it was zero acceleration because it was twice the acceleration in only half the time, and therefore it was no increase in acceleration. You don't even understand the argument, Gus. So either, be more informed, and quit lying about what has been stated already in videos and what hasn't, So you either watch some of the videos and then you can talk shit, or you make a direct point that you can reference to some authority saying so. You're not an authority. You can't just make statements. You have to prove that your statements have some sort of credibility. I'm not going to just waste my time debunking your assertions that have no evidence backing them up. So if you're going to keep doing that, you're either going to be timed out or just blocked. Oh great, right off the bat we have a troll. Very pathetic. Well, whatever. Anyone who offers criticism or a counter-belief is a troll. Now, that's obviously a lie. I play a substantial portion of their videos, and I read a substantial portion of their content. They won't play any of my arguments and counter them one by one. I have them in videos where it's just the whole beginning of the video is just a resuscitation of all the arguments against what they say. They won't play my MGT video. They won't play my description of a lever. I've asked them for 2 years. For 2 years, I've said, draw a lever on the board and explain how it works. They won't do it. All right. Offers as a troll. No. You're showing the definition. A troll is just someone who keeps pretending something hasn't happened that already has happened over and over again. Don't agree with someone but can't say exactly why. Just call them a name. No, you're the one who can't reference a single statement by an actual scientist defending anything you're saying. Okay. Just label them something bad, so this is just a waste of time. So you don't have to actually deal with anything that they say. A label doesn't matter here. Who cares? You can call anybody you want to an asshole. That's fine. You're making assertions about what science says. That's the part that's not just fine. Because you're a fucking liar. Okay? You don't have any evidence of this crap. Okay? And it doesn't do what you say it does, which proves the case. All right. Do you have a YouTube channel, Gus? Well, obviously he has a YouTube channel. If he's, posting comments, just go to his channel. But I'm sure it's not a channel with any content. All right. His experiment is precise. So what's the point, right? I mean, I just showed how the spring is actually flying up with the object. And he says, no, it's a really good experiment. He collected all the energy. I just demonstrate how, a quick release isn't saying, say if I release something by pulling my finger across the edge. If I put a metal tip on my finger and then pull across the edge again, I haven't improved the release system any. Quick release is a kind of engineering target. You're trying to get to a certain point where you're, eliminating any kind of degrade or slowness in the process of the release, or however you want to describe that. It's a certain thing that has a qualified definition. What he did doesn't qualify, because all he did was turn a finger release into a AI release. He created a mechanical release, not using a feeling, touchy finger, but it's still just as slow. Okay, anyway. Let's see. Empty feelings, do you have a job? Okay, we're just going to block him. He's really not doing anything useful here. I mean, it was a simple enough question. Do you make videos on YouTube? Do you have a channel? I mean, that's not too much to ask from somebody, right? No. Okay. If you have a YouTube channel, make a counter argument. So, yeah, clearly not a very demanding task, right? Let's just understand, if I could make videos, right, and I'm supposed to be a retard, why can't you people handle it? Okay. If gravitational force pulls in meters, then am not understanding how it's determined by time. Well, you don't understand that it's meters per second. Yes, it's a number of meters of a rate of velocity. If I say you're going 60 miles an hour, I'm not saying you're going 60 miles, and I'm not saying you're going an hour. I'm saying you're going 60 miles as an average per hour. All right, so I don't know where you're confused, but the per second is the key word. You only get to 9.8 meters after you've traveled a whole second. And if you're fighting it, you have to go a whole second in the gravity against it before you have encountered 9.8 meters worth of resistant pressure. Well, yeah, you can't really help some people. Especially people who call themselves blade of grass. Yeah. Okay. So yes, someday you hope to be, a weed. you know. I just, just a full-grown big weed. Maybe someday he hopes to be like a hibiscus bush or something. Long, long, long time from now when he's really grown up. Ugh, just is pathetic. It really is just horrible. The internet. If they did the internet right, it would have had a system of accountability, and everybody would be accountable. You'd have one screen name to start on the internet, and that's it. You wouldn't be able to have 5 zillion different accounts and all that kind of bullshit. And you'd have to be accountable for all the crap you say, and everything you say would be rated by people who over time are tested to be very good at pointing out who's just a troll and an asshole and who's dishonest regularly, on a regular basis, says things that aren't true. And all of that would be part of your reputation on the internet. So we just see the word Gus and we'd see every little crappy post he made. We'd be able to go analyze what his past behavior has been. But we don't have the accountability net. We have the unaccountability cheater net. Because all these little weasels can't make a stand-up argument. They can't have a stand-up fight. They have to cheat their way. Yuck. Disgusting. Alright. So, I don't know if I want to leave the captions on or not. I guess it doesn't hurt that much. Alright, so this is, I can't remember his name, Shakar, okay, or Shankar. Really smart guy, blah blah blah, all that kind of crap, and let's see, and what to say, but really a mathematician, frankly, okay, really a quantum physicist, and he's doing the whatever you want to call it, fundamental physics thing, just because I guess they lost the professor and he had some other position, and they just said, please, will you do the course, because nobody else can do the course. And so he agreed to do it, and he did a pretty good job. He's personable, a little bit of wit, very dry humor, frankly, but whatever. Okay, so in this portion, he's trying to get to the point where to do any of these Newton's laws things, you have this formula, F equals ma. Well, how do you measure any of this stuff? How do you measure a force? How do you measure mass? Let's say if you have no gravity, you have no way to, compare it to some other thing like that. What do you do? And so the argument is you use a spring. You use some device that has a consistent capacity to provide a certain amount of force, and that'll do it over and over and over again. And now you can do this mass comparison thing, because if you don't have gravity, you have to use some kind of mechanism that allows you to impose a force. All right, that's sort of what he's getting to. I don't hear anything. It's not good. Yeah, it's really bad for business if there's no volume. I think he's listening. Oh, that's what he's doing. He's listening to one of the students. Okay. Still listening. He's a very good listener. Oh, no, here, now he's listening.
Let me repeat what he says. Take a spring to outer space.
Okay, so I'll take the speed and put it back down. Well, I'll put it to 125. So you take the spring and you put it in outer space.
And we'll hook up some objects to them and see how fast they move and do a comparison. That's fairly close to what I had in mind.
So he just said it's fairly close to what he had in mind. So you just take a spring, you compress the spring, and then you can see how much something weighs based on how fast it goes. So that's the words he used, fast it goes. Okay, how fast it moves. So, and now he's going to basically use the precise word of acceleration, but clearly he is using the word acceleration in the net form. That is, and he even says later in the video, which I probably won't get to, that what Newton says force equals, he's saying total force, because that's where you've broken it, right? Because Newton said, if you want to know the rate, you do F equals the change in your momentum divided by time. That's what Newton actually wrote. He didn't write F equals ma. But if you want to know the total force, you don't bother with the time component. You're just saying what's the change in the momentum. That's it. You don't need any other time component. You're just saying the force equals the momentum. And I read Newton's words, okay? I read it 3 days ago. Clearly, he said it. You want twice the motion, double the force. You want 3 times the motion, triple the force. Clearly.
But it's not the word perfect answer. And I just want to take some time thinking about it. Yes. What do I learn from the period?
So he's just the period obviously would be controlled by gravity, so that's not going to work in space. And he should have just said, fuck that, I'm not going to learn anything, but there's no period, because we're talking about a place where I can't use gravity.
How? Remember, you cannot peek into chapter 6 and 7 because you've seen it before. I'm asking you if somebody wrote apparently Shakespeare's plays for it.
All right, so he's talking about the period of the oscillation. So if you pull the spring, the thing will oscillate. Well, you don't need the oscillation, because the oscillation in space, and if the spring was non-frictional, the oscillation will be 100% of the energy. It'll just keep oscillating forever. So that's not going to tell you anything.
It's one of the rumors, right? Suppose Newton comes to you.
But the speed of the oscillation will change with the mass. So if you change the mass, you'll change the speed of the oscillation, the velocity. And that you can measure.
And says, I have this great.
And no one's going to say you change it by 1.4.
Law. But I don't want to publish it under my name. So I'm going to give it to you. And you have got this new law, but how are you going to sell this, right? You got to tell people how to use it. And you realize it's very subtle, because the very first thing in that equation, which is m, is not yet being defined. And he gave an answer which is fairly close. Doesn't rely on gravity, doesn't rely on the planet. Now you cannot say to me, take a force due to a spring and see what force it applies and divide by the acceleration to get the mass, because we haven't defined force either. You got to realize that. Let me ask you something. How do we decide how long a meter is? Can you tell me how do we know how long a meter is?
So this is all kind of rudimentary. Like I said, it's not a very good video, blah, blah, blah. A lot of bullshit in here that's, not very useful. Obviously, it doesn't matter what you define as the unit. Doesn't matter. It doesn't matter whether a meter's 10 tons. It doesn't matter whether a ton is 4 meters. It doesn't matter what words you're using. It just matters for comparison, and everything else will be based on a comparison, a number of those things. So you'll say 10 meters. You're just saying 10 elephants or 10 chickens. You're just saying it's 10 units of something you do know.
Right. And we will call it. First thing you got to do is that some of these things are not God-given. A meter, for example, is not deduced from anything. Napoleon or somebody said the size of my ego is 1 meter. That's it. That's the new unit of length. You take a material like silver, put it in a glass.
Well, it actually was more logical than that. I think the meter started off being the length of an arm or something. So,
Last case, and that's the meter. That's the definition of a meter. That's not right or wrong. Then I ask you, what is 2 meters and what is 3 meters? We have ways of doing that, right? Take the meter and put it next to the meter. That's 2 meters. Or cut it in half, or use some protractors and dividers and compasses. You can split the meter into any fraction you like. Likewise, for mass, we will take a chunk of some material and we will call it a kilogram. So I should give you some hint. So that kilogram, I don't expect you to deduce. That is a matter of convention. Just like 1 second is some convention we use, and 1 meter is some convention.
Right. So what he's ultimately going to do here is just suggest you put the 1 meter on the spring. Okay. And now you can use the 1 meter to decide how much force there is, and you can, and then everything else you put on the spring will proportionally change in terms of its velocity, and so if you want to know something that weighs half as much, it'll go twice as fast.
Use. So I'm going to give you a little help. I'm going to give you a glass case, and in the glass case is an entity which is 1 kilogram by definition. Yes, then I give you another object, elephants. Here's elephant, and I'm telling you what's the mass of the elephant. How do you find its mass? You got to take the hint he gave. I give you a spring and an elephant. What should we do? Yes. No. Remember, when we hang the elephant in outer space, nothing's going to happen.
Right. So he's talking about weighing it, by stretching a spring. Yeah, that ain't going to work because you don't have gravity to pull on the elephant. So without the pull, it ain't going to work. And without the push, you can't compress the spring either. So without gravity, you're not going to get any weight. You're not going to get a measurement of weight. You have to give it energy for you to weigh something. This is the irony. Momentum is weight. Gravity gives you motion into the earth. That's why you can deflect the scale, is because you're moving. Just like if you were moving sideways. Now I've provided that argument at least, 27 times now? Where's the counter argument explaining how it doesn't work that way? That my motion sideways wouldn't be just the same as duplicating my motion into the earth. That I can create a sideways motion that would be exactly the same as the 9.8 meters of motion that causes my gravitational weight. And that if I put the scale sideways, I can weigh exactly as much as my actual gravitational weight.
Right. Okay.
Alright, so the good thing about the captions, it can actually hear what these other people are saying, which is inaudible. Alright, so the guy's saying you pull the elephant on the spring and you see how it oscillates. Should be proportional to how from the resting state of the spring. So the velocity should be proportional.
When you say push the elephant, you want to push it a particular way? Or what do you want to do? That is correct, but you don't want to give it a definite push. Yes?
So he's really saying you want to compress the spring. You don't want to push the elephant into the spring, which isn't a huge distinction, frankly. You want to compress the spring and then a certain amount, and then test everything on that same spring compression. The Brozo experiment. You push radially on the axis of the spring because you know that the centripetal force, this won't work, so this guy's going to get shot down.
Yeah. Or maybe that's an interesting thing, but that's correct. You can do that too, but let me...
He was talking about swirling things.
Now, put you out of your suspense. I think I've heard bits and pieces of the answer everywhere, so I don't want to wait till we get it word perfect. The point is, the 1 kilogram is a matter of convention. We want to know what is the mass of the elephant. So we can do the seesaw experiment you suggested, but the seesaw experiment requires gravity. So we don't want to do that. So a spring will, on the other hand, exert a force. We don't know what the force of a spring is. If you assume that, you're not playing by the rule because we don't know what force it exerts. But we do know it exerts a force. So here's what you do. You hook one end of the spring to a wall and you pull it from rest by some amount.
Right. So this is the part where they're implying that this professor is actually going to be saying this is 1.4 effect. Even though he's going to overtly show the same Lewin kind of proportionality. So the velocity, the acceleration is proportional to the change in the mass. We're supposed to believe he didn't mean to imply that, yes, the half mass goes twice as fast. Which he clearly does. What the hell is that sound? Some fucktard's always doing something stupid. Ugh. It's a neighborhood full of fucktards.
And you attach the 1 kilogram mass to it. Yes?
Let's see, though, is if we're in outer space, where are you going to attach to? Okay, so now he's going to bring up a point that I've made before in a way. Like in space, you can still make an object that's really, really heavy, and for all real purposes, it's not going to move. Okay, so I do have to pause for a second. Alright, I should be back. Annoying neighbors. Anyway, alright, where was I? Okay. So the kids basically bring up the point, the student, that you don't have anything to attach to in space.
A wall that will not move? Well, no, you're right. What can actually happen is that if you're in an enormous laboratory, which is made up of an enormous object, then you will find that you can, in fact, attach it to the wall. You can go to outer space. No, it won't move very much. And we can, once we know enough dynamics, we can understand.
So, he's saying it's not really explicitly true, but yes, it's spread out. The velocity that you're going to create is so tiny, okay, that it can't possibly affect the other side of the experiment because the motion is going to have to accept the energy at such a slow rate that everything that's going to happen is already going to be well past happening before any reflection or any kind of effect of the other side not accepting the energy well could be realized by the other side of the spring. Something like that.
We can answer your question.
The center of the spring won't be moved, which is really the point. The center of mass of the spring won't move.
Does outer space even rob you of something to which you can anchor a spring? Answer is no. You can anchor things to objects in outer space.
So it's really not a very perfect anchor, though, clearly. But it's just, we're already in that circumstance now. The Earth isn't a perfect anchor. It's just a fact that it will move tiny amounts.
This won't act the way gravity does, but you can nail it to the wall and pull one end. So you pull one end. We don't know what force it exerts, okay? But it exerts some force. Now I tie this 1 kilogram mass to it. I let it go, and I find the acceleration. That is the force, which I do not know in magnitude, okay?
So when he says he finds the acceleration, he's saying you find the velocity. So we're testing the 1 kilogram. Whatever way we're going to test acceleration, we're basically saying we're going to see how fast it goes. So it's just a lie to pretend the acceleration in this case is anything other than the end velocity. It started with 0 velocity. We're going to see how much velocity it ends up with, and that will be exactly the acceleration. There's no confusion here. There's no pre-existing velocities to account for. It's just going from 0 to some end velocity, and that will be exactly what the acceleration is. So again, they will try to lie and say he really means 1.4 here. No, he doesn't. He's saying quite explicitly, you just measure how fast the damn thing goes. You see how much motion it has.
But this is the acceleration of the 1 kilogram mass. Then I bring the elephants.
A equals
and I pull
F.
the spring
Do
by
you
the same
understand? He's saying A equals F. It's a direct comparison. Not A over some time, not A something else. It's A equals F. This is a 1 for the 1 kilogram. Jesus.
amount, and I find the acceleration of the elephants. And the denominator is obviously the mass of the elephant.
And the mass will be in units of this 1. So it's going to be 2, 3, 4, 5, 6, 7. And obviously the acceleration is going to have to go down as the mass goes up.
The force is not known, but it's the same force. So when I divide these two numbers, I'm going to find A1 over AE is equal to ME over M, which is the 1 kilogram mass. So what we needed was some mechanism of
So he's just inversed and saying these are proportional. So the 1 is the ME. So you're just saying what's the mass, that'll tell you the acceleration. So if it's 1 mass, then it's 50 miles an hour. If it's a half mass, it's 25 miles an hour. There's no squares in here, right? We don't see anything squared, or we don't see any square roots.
exerting some fixed force. We didn't have to know its magnitude. But the acceleration it produces on the elephant and on the mass are in the inverse ratio of their masses. So if you knew this was 1 kilogram, then the acceleration of the elephant, which will be some tiny number, maybe 1/100th of what this guy did, the mass of the elephant is then 100 kilograms.
So he just made it clear, right? He just told you it's 100 kilograms. He just deduced it based on its acceleration, how fast it's going to go. So it gave you the answer. So where in here was there any 1.4 crap? He's basically just saying half the mass, twice the speed, twice the mass, half the speed.
Now there are again subtleties even here. If you think harder, you can get worried about other things. For example, how do I know that when I pull the spring the first time for the mass, it exerted the same force when I pulled the spring the second time for the elephant? After all, springs wear out.
Right, so this doesn't mean much because, so he's going to say springs wear out. Yeah, you do it 10 times, and if it keeps coming up with the same answer, then you know your spring's working pretty well.
That's why you change your shock absorbers in your car. After a while, they don't do the same thing. So first, we got to make sure the spring exerts a fixed force every time. You can say, how am I going to check that? I don't have the definition of force yet. But we do know the following. If I pull the 1 kilogram mass and I let it go, it does something, some acceleration. Then I pull it again by the same amount and let it go. I do it 10 times. If every time I get the same acceleration, I'm convinced this is a reliable spring that is somehow producing the same force under the same condition. On the 11th time, I pull the mass out and put the elephant in. I have some degree of confidence I'm working with a reliable spring, and then I will get the mass of the elephant. Why is it so important? It's important for you guys to know that everything you write down on the notebook or blackboard as a symbol is actually a measured quantity. And you should know at all times how you will measure anything. If you don't have to measure anything, you are doing algebra or trigonometry, you are not doing physics. So this also tells you that the mass of an object has nothing to do with gravitation. Mass of an object is how much it hates to accelerate in response.
So he just said how much it hates to accelerate, right? But that's really not what it's hating. It's just a simple argument that if it has more atoms, you're going to have to push more atoms. Okay, so that's it. I mean, it's not saying I won't accept the energy, I won't cooperate. It's merely saying that if you have a tiny amount of energy and I have to spread it over a huge number of atoms, I'm not going to get much velocity. The velocity is the thickness of the energy spread on the mass. So you can just think of it that way, that you just have bread, which is the mass, the butter is your velocity, and obviously if I have more bread, the butter's going to be thinner, and if I have less bread, the butter's going to be thicker.
Response to a force. Newton tells you forces cause acceleration, but that acceleration is not the same on different objects. Certain objects resisted more than others.
So what he's saying is the only resistance they can provide is based on their mass. The more mass they have, the harder they are to push. The less mass they have, the easier they are to push. So when he's saying this, it sounds like different objects. He means something other than different masses. All he means is different masses. Nothing else.
They are said to have a bigger mass. And we can be precise about how much bigger by saying if the acceleration of a body to a given force is 10 times that of a 1 kilogram mass, then its mass is then 1/10 of 1 kilogram. This is how masses can be tabulated using a spring. So imagine then, from now on, we can find the mass of any object, right? We know now with the same spring.
So again, he couldn't find the right mass of the elephant if he didn't use this proportional momentum lever kind of argument, where all you're basically saying is I increase the mass, I increase or decrease the velocity, and I decrease the velocity proportional to how much masses I have to push. So where in here is there any indication of the 1.4 theory?
By this comparison, we'll find. So all objects now can be attributed a mass. Then we may, from this equation, say a certain force is acting in a given situation by multiplying the m times the a. But then, here is what we actually do. Now we go back to the spring. We go back to the spring, and we want to learn something about the spring. We want to know how much force it exerts when I pull it by a certain amount. Now I can measure that, because I pull it by 1 centimeter, and I find the acceleration it exerts on a known mass, that m times a is the force the spring is exerting. Then I pull it by 1.1 centimeter, and I find MA. I find 1.2, I find MA. I draw a graph here of the amount by which I pull the spring versus the force it exerts. And
so he's going to draw it, differently than most. So I guess he just likes being unique. So he's going to draw it in the Z axis, which is unlike I've ever seen it drawn before, which is just kind of funny.
it will typically look like this, and the formula we say is F equals minus kx, where k is called the force constant.
So usually, okay, it's drawn as a line this way. Okay, a straight line. And it has, it can have a bend at the beginning and it can have a bend at the end where the spring's tolerances break down.
You've got to understand what the minus sign is doing here. This is the force exerted by the spring on the mass. It says if you pull it to the right, so that x is positive, the spring will exert a force which is in the negative direction. That's why you have a minus sign.
Right, there's no minus energy, so the whole thing is a little bit sloppy, frankly.
And then all springs will do something like this. Further out, they can do various things. The force may taper off, force may not be given by a straight line, but for modest deformations.
So modest deformations, again, so he's saying in the middle, everything works pretty reliably.
Every spring will have a linear regime in which the force is linearly proportional to the spread.
Linearly proportional, so again, the argument is kind of clear. It's going to give a linear result, okay? Half the mass, twice the velocity.
It also tells you that if you compress the spring, compress it means x is measured from this position where the spring is neither compressed nor expanded. So x is not really the coordinate of the endpoint. You've got to understand that. Springs have a natural length. So x is measured from that length. If it's positive, it means you stretched it. If it's negative, it means compressed. And this equation is telling you if you compress it, namely if x is negative, F will be then positive because it's pushing you outwards. Therefore, what we have done now is we can take all kinds of springs and we can calibrate the force they will exert under various conditions. Namely, if you pull it by so much, that's the force it will exert. So I want you to think for a second about two equations. One equation says F equals ma. Other equation says F equals minus kx. So what's going on? I mean, is one of them Newton's law? Then what's the other one?
So no squares to be seen. So let's just understand that when you're doing the Newtonian type momentum analysis, there's no squares here. The x isn't squared. Okay, so it's perfectly valid, apparently.
Maybe F equals minus kx should be called Newton's law. Why is F equals ma called Newton's law? Then what's the meaning of...
Well, and it's called Newton's law when it's not Newton's statement. So let's just understand again, it's not what Newton said. So this is part of the canard, okay? What Newton basically said is F equals mv. Now, obviously, in all of these circumstances, A is going to be the same as V, okay? If you start with something not moving and you make it move with the force, obviously all the acceleration will produce all of the velocity because you don't have some pre-existing condition. So you're saying, what's the force changing something? The changing force will be the change in the acceleration. The change in the acceleration will be exactly what you have in the end result of the velocity. And it's the net product. You want to know the total force that was affecting something, then you have to say, what is the net change in the velocity? And it's going to be the answer. That's the acceleration, because you don't have to worry about anything else. So it's just so obvious how this is all just so distorted, and just using the stupid A term allows them later in the mathematics to sit there and square the A for absolutely no reason. No logic, no nothing, because they want to say it's per second, and they somehow say it happens per second by saying that the seconds are squared. How is that per second? How is that notation representate per second? Squaring does not represent per second for, it could be 3 seconds, it could be 10 seconds, it could be 100 seconds, it could be 1 billion seconds. How does squaring answer all of those circumstances? Obviously cannot.
This expression. What's the difference between saying F is minus kx and saying F equals ma? They're saying very different things. Yep. Right. Let me repeat. F equals ma is universally true independent of the nature of the force acting on a body. And then,
Well, and obviously the kx is only with springs, but yeah, so what?
very good. That's the whole point. So the cycle of Newtonian dynamics has two parts. First,
So you can just pick anything you want. So gravity, you can use a different formula and just put the g where the k was. So instead of kx, it's gx. And instead of x, you can put gm. Which doesn't mean much, really. I mean, it's all kind of just bullshit.
one says, if you knew the force acting on any body, without going into what caused,
If you just understood it all motion as momentum, as Newton did, you already automatically can do all of that because you're just looking for the mv. You're just looking for what is the mass and the velocity. And if I want to know a force that changed something, well, I'm just looking for the velocity portion that happened while the change was taking place. What portion of the velocity was changed? Well, that's the part I'm interested. I just do mass times the velocity that was changed, and I have the momentum change. So again, this is all just such, this isn't complicated, and they've made a mess of it. Newton was pretty simple, and they've turned it into crap with their F equals ma crap.
the force, then you may set that force equal to the mass times acceleration of the body. We think of force as the cause and A as the result.
Right. And then you see, could have just written right down here. You could write F equals, and then you just look for the mass and gravity. So you could just put gravity here. Or, so you could do mg. F equals mg. And I could just use also F equals mv. Because the velocity is the same as the gravitational constant. If I'm in the gravity for 2 seconds, I know exactly how much it's going to be. It's just multiplying the gravitational constant times how much time. So it's just mgt. mgt is exactly the same as mv. So I could just write another F equals mv. And it would be just as legitimate as either one of these.
Or the effect. Force causes acceleration, and this is a precise statement. There,
Force causes a change in velocity. And if you went from 0 to a new velocity, then the entire change will be the acceleration.
Newton doesn't tell you what forces are going to be acting on a body in a given situation. If you leave the body alone, maybe there's no force acting on it. If you connect the body to a spring, which is neither compressed nor extended, there's no force acting on it. If you pull the spring, there is a force acting on it. Newton is not going to come and tell you what force the spring will exert when it's pulled by some amount. That is another part of your assignment. So the physicist has to constantly find out what forces act on bodies. That's a separate exercise. In every context in which I place a body, I'll have to know what are the forces acting on it. I've got to find them by experimenting, by putting other bodies and seeing how they react, and then finding out that's the force that acts on a body when it's placed in this or that situation.
Well, anyway, I don't think these statements he's making are explicitly true. The fact is that you can find one thing by just analyzing the other side of the equation and finding out what it is that half mass do, and then just saying, well, I know that twice mass is going to do twice as much.
Once you got that, then you come back. So in the case of a spring, this is the law that you will deduce. If it's something else, you will have to deduce another law. For example, we know that if a body is near the surface of the Earth, the force of gravity and that object seems to be m times g, but g is 9.8. That's something you find out by experiment.
Right, and the more accurate way to say it is mgt will tell you the total of this. It won't tell you the gravitational rate. So this mg will tell you some sort of rate, but the more explicit statement is just say mgt, because the time will tell you how many clumps of this g you got. But that's all. This is just saying mv. It's just telling you what's the velocity. The velocity at the rate that 9.8 meters. So we have 9 meters, small g, 9.8 meters. You know that the actual force complete will be how many minutes or how many seconds did you fall in the gravity. So you multiply it by the time. And it's just going to be the mass times the velocity, because the g is going to end up being your velocity. G times 1, G times 2, G times 3, G times 4. So if you fall for 4 seconds, it's 4G worth of velocity. So it's 4 times 9.8. That's your velocity, your total velocity. And that's exactly what your energy is going to be, times your mass.
So every time you're finding out a different force that's acting on a body with different origin. One says, leave any body near the Earth, it feels a force. I know this is the right answer, Because if I now find the acceleration, I find it's mg divided by m, and I get minus g as the answer for all bodies. By the way, that's a very remarkable property of the gravitational force, the cancellation of the two m's.
Yeah, well, and he's basically going to explain, yeah, because the force is proportional to the mass. You get more force, more mass, you collect more force. Less mass, you collect less force.
If you look at the electrical force, the force of, say, the proton and the electron or something, is not proportional to the mass of either object. It's proportional to the electric charge of either object. Therefore, when you divide by the mass to get the acceleration, the response to different bodies is inverse to the mass. But gravity has the remarkable property.
Yeah, well, gravity and electric charges are on different scales of the universe. One the tiny scale, the other one the very big scale, not the same thing at all. Blah, blah, blah.
That the pull of the Earth is itself proportional to the inertia of the object. So when you divide by m, m cancels, and everything falls at the same rate.
So by inertia, he just means mass. So
in fact, it's a property of gravitational fields anywhere.
Mass doesn't, inertia doesn't mean anything if you understand. It's just the mass. The big masses are harder to push than light masses. Not the other way around, by the way, Ian. Yeah, lighter masses aren't got more inertia.
In outer space, where there is some residual field due to all the planets and all the stars in the universe, that the force on a body is proportional to the mass of the body. So when you divide by the mass to get the...
Okay, so the force on a body is proportional to the mass of the body. And so he's basically just saying right here, it works for gravity, it would work for the spring, it would work for anything else. These are all the same formula. So he's basically telling you that proportionality means it's a real thing. And because it works in gravity, it'll work with a spring.
Acceleration, you get the same answer. Everything, gold, silver, diamonds, particles, everything accelerates the same way in a gravitational field.
So accelerates the same way. So let's understand, he's not dodging. This acceleration word doesn't mean because it accelerates faster, it moves faster, okay, that somehow it has more or less velocity. He's clearly saying the acceleration is completely proportional to the mass. It's directly connected.
Due to this remarkable fact. And this was known for a long time, but it took Mr. Einstein to figure out why nature is behaving in that fashion. If I have some time, I'll tell you later. But there are two qualities which happen to be equal. One is inertial mass, which is how much you hate your velocity to change.
Okay, so again, he says how much you hate your velocity to change, when clearly it has nothing to do with how much you hate. It's just the fact that you have so much butter, you're spreading it on so much bread. There's no hating. In space, it will absolutely move, even a tiny amount. So you could you throw a pea at the International Space Station, you can make the International Space Station move. It will move. It will not move. It will not say, I hate moving. It just won't move very fast.
How do you resist acceleration? That exists far from planets, far from everything. Other is gravitational mass, which is a measure of how much you're attracted to the Earth.
So same mass. Okay, gravitational mass in 9.8 meters is what we use, and so those masses are equal. I mean, it just is the fact that we have made our comparisons to something falling in gravity and called weight, that equilibrium. Mass equals your 9.8 meters per second is what we're using as the kilogram.
There's no reason why these two attributes have to be proportional. They're proportional and they're equal by choice of units. And you can ask, is it just an accident or is it part of a big picture? It turns out it's part of a big picture. And all of general relativity is based on this one great equivalence.
Okay, so there's no point in saying that crap because this great equivalency principle is a pile of shit. But anyway, obviously gravity's fight different than the Earth pushing you back is a very different force than gravity. They're not equivalent forces. One pushes chemistry, one pushes nuclear bits. One's a nuclear force, one's a chemical force.
Quantities with very different attributes. Why should the amount by which you're attracted to the Earth be also a measure of how much you hate acceleration? Two different.
So again, we don't hate acceleration, so it's just more nonsense. Nothing hates being accelerated. It's just that, frankly, if it's a big truck, you need a lot of gas to move it.
Features, but they happen to be the same. Anyway, what physicists do is they put bodies in various circumstances and they deduce various forces. This is the force of gravity. This is the force of the spring. Here's another force you might find.
So this will be, we'll start getting into the crap zone soon. Okay.
Put a chunk of wood on a table and you try to...
So now he's going to call friction a force, when no. It's just you losing your force. You're losing your energy. You're heating the surface. You're changing something else. you're giving your force away. There's no friction force.
Move it at constant speed, then you find that you have to apply minimum force. We are moving at constant velocity. That means
So he's talking about kinetic versus stagnant. So when the fact is the friction changes by who knows, a variable coefficient based on the substance. So the amount of energy it takes to move it will be different than the amount of energy required to keep it moving. So the initial energy has to be a little higher than the sustained energy. So if you want to go 30 miles an hour, you have to really make it go 33 miles an hour first, and then make it go 30 miles an hour. So it's basically in a hole, and you have to push it out of the hole, is, I think, the more rational way to understand it. It's bound with the material, it's stuck to it, and you have to break the glue before you can move it.
means the force you're applying is cancelled by another force, which has got to be the force of friction. So force of friction is yet another force. Then there are other forces, right? You guys know there's the electrical force. If you bring a plus charge near a plus charge, if my body M has a plus charge and another plus charge is there, it'll feel a force due to that. That's not going to be given by Newton. So Newton did not ever tell you what the expression for force is in a given constant. That is a constant study. Coulomb discovered the Coulomb's law, which is the repulsion between charges. And nowadays we know if you go into the neutron or proton, there are quarks. There are forces between the quarks.
All right, so there's really no point in all that crap, right? Because we know that's not necessarily true at all. I mean, they really don't have any evidence for all that crap. Okay, so, let's see, blade grass. If gravitational force pulls in matter, then I'm not understanding how it's determined by time. Okay, I already answered that. So, yeah. Sorry, too stupid, frankly. It's saying right to you, per second. There's something that happens per second. When it says per second, it's making it pretty explicit. Whatever happens, happens per second. When you say a bigger truck needs more force to move it, it has more atomic particles. You have to spread a certain amount of little BBs, and you have to spread them across more particles. So it's like money. It's like pennies. You're putting a certain number of pennies in. You have a certain number of piggy banks. Obviously, there's going to be less pennies in each piggy bank the more piggy banks you have. So the more piggy banks you have, the less pennies per piggy bank. Kind of, Come on. I mean, you're smarter than this, frankly. When you say bigger truck needs more force to move it, isn't Haight's acceleration just a sloppy way to say that? Well, I think it's insanely sloppy, frankly. It obviously doesn't not want to be accelerated. It's not resisting accelerating. It's just saying you have to give me enough money. If you don't give me the money, I can't go as fast as you want me to go. It's not going to happen. It's like giving people enough food. Starving people aren't resisting being fed, but if you give 10,000 people one slice of bread, I mean, each person's getting such an infinitesimally small amount of calories, they're not going to survive. So the fact that you haven't given them enough to live, it doesn't have anything to do with their willingness to be fed. They're not resisting being fed. You just didn't give them anything to eat. I mean, shit. I mean, to me, it's a lot more than sloppy to imply that somehow the starving people are making it difficult. And they're just saying, I'm not going to eat your food. They're not doing that. All right, so I guess we'll apply some sort of 3-minute, 4-minute warning, 2-minute warning, something. But yeah, I don't need to play any more of this to have made my points, blah, 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 blah. If you don't have something else to talk about, then we won't talk about anything. I'll just get the hell out of here and blah, 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 blah. Okay, but the bits that don't get force, everything has to share, okay? The fact is the electrons guarantee that. So the force is spread through the electrons at the speed of light through an object. That's sort of how it takes place. Well, technically it's the speed of sound. So a piece of steel shares its energy at the speed of sound in steel. So that's sort of been proven. So it moves, one end does move before the other end moves. It happens. The steel actually, you hit it and it actually compresses, and then it, re-expands as it moves. That's the way it works. Let's see. But if the bits don't get the force, resist the other bits that did get the force. So again, you're just not thinking about it correctly. There's no way that they all don't share in the end, and you're really just talking about the speed at which they can share. So this is like when you have the string, and then a weight, and then another string. All right, and you're going to play this game where you're going to say, what string am I going to break? Well, yeah, you can break the bottom string, okay, by going fast, because the top spring won't know you pulled, because it's going to take too much time for the knowledge of the extra pressure to get to the top spring, and so the bottom spring will break, right? But if we pull slowly, then the information can get to this string, and this string can say, you're making this really, really heavy, okay, I can't take it, I'm going to break. So we know there's a speed limitation to which this energy is filtered to all the banks, and that's my whole point, is that the thing that slows it down, that's why the Newton's cradle doesn't work with uneven masses, because the Newton's cradle needs the information to go in just once. There can't be any bouncing around and reflection. There's no time for that. So if they're the same mass, the energy just goes right in one and right into the other and completes, because this one can go exactly the same speed. It doesn't have to bounce around inside the second object to get everything moving the same speed. The unevenness of speed that'll happen, and you have to say, okay, yeah, you're sort of right. Part of the object is going to be having more force, more pressure than another part, and takes time for it to bounce around inside the object and even out the pressure. Well, the Newton's cradle isn't providing that time. So that's why the two mass can't make the one mass leave with twice the velocity, is because it doesn't have, there's not enough time for the reflecting to take place that needs to take place to convert the pennies into nickels, so to speak, to increase the velocity, because you have more of it. I don't know how to say that. To go through all the banks with the second penny. If they're just putting one penny in, it goes very efficiently. If they have to go back and put a second penny in, it doesn't go so efficiently. And if they put a third penny in, it's even more inefficient. So the more pennies they have to go back and put in one at a time. They can't put all the pennies in at once. They have to put them in one at a time. And that's the part that makes conversions between different masses difficult. And that's why levers are so cool, because they do the conversion. No, I guess I should see how many people are here just out of curiosity. Blah, blah, blah. Things don't seem to change much, but, it's the internet. 13. Well, it's almost 10 o'clock, so 13 is pretty mediocre, even though it's a shorter live stream, I think. It's only an hour. Oh, an hour and a half. That's pretty long, actually. Yeah. All right. So we'll see if there's any other comments, and if nobody has anything else to say, then it will be the end and such. And so forth and whatnot. Alrighty then. So, yeah, well, we just have to keep playing with this. I keep searching for, the simple experiments being performed, but there really aren't any basic physics experiments on the internet. Quite irritating. Busy morning here, so I've got nothing else. Enjoy the weather if it's nice. Yeah, well, not for another day or two, but whatever. It's whatever that thing was. I mean, they really ought to have a name for some storm system that just sits around for 2 weeks on top of you and swirls around like a hurricane, except really slow. Yeah, so they ought to call it something. I mean, it wasn't technically a tropical depression, but I don't know what the fuck it was, but it was pretty depressing. So they should just call it a depressing. A depressing. Shit. 2 weeks of gray, wet, cold. Kind of irritating. Especially me being a gardener. It just kind of ruins all the fun. Anyway, so till the next time, and such and so forth and whatnot. 10-day forecast says I can put tomatoes in the ground. Yes. Mine are half and half. Yeah, they're half in the ground. They're close to the ground, but they're not in the ground. Anyway, till the next, it's the nighttime temperatures, you gotta watch that. So you don't want anything below 50 degrees or just kind of stunts growth. So you have to try to keep the shit from getting too cold at night. Anyway, till the next time, and such and so forth and whatnot.